You think you know what time is. You've lived with it your entire life. Every second, every minute, every hour. Time is just there, right? It flows forward like a river, the same for everyone. Absolute, universal, constant, wrong, completely wrong. And Richard Feynman spent years trying to get people to understand just how wrong. Here's the problem. You can't actually see time. You can't touch time. You can't measure time directly. What you measure are changes, events, motion. A clock doesn't measure time, it counts oscillations, the swing of a pendulum, the vibration of a quartz crystal, the oscillation of cesium atoms. We count these events and call that time. But Feynman would ask, how do you know those oscillations are evenly spaced? You check it against another clock. And how do you know that clock is consistent? You check it against another. It's circular. We measure time by events and events by time. There's no master clock, no absolute reference. And here's where reality gets strange. What if those events don't happen at the same rate everywhere? In 1971, Joseph Harfello and Richard Keating took atomic clocks, the most accurate timepieces ever built, and flew them around the world on commercial airplanes. When they landed and compared them to identical clocks that stayed on the ground, they disagreed. Not by much. A few hundred nanoseconds. But measurably, undeniably different. The clocks that flew experienced less time. How is that possible? Because time itself runs at different rates depending on how you're moving and where you are in a gravitational field. Feynman explained it simply. Time is what clocks measure. And clocks can disagree, not because they're broken, but because time itself is different for them. There is no single time. There's your time, my time, the time experienced by that airplane, the time experienced by a satellite. All different. This is time dilation, and it's not philosophy. It's measured reality. Let me show you why this has to be true. You're sitting still right now, but not really. Earth is spinning at 1,000 miles per hour, orbiting the Sun at 67,000 miles per hour. The Sun orbits the galaxy at 514,000 miles per hour. Motion is relative. There's no absolute rest. Now here's the weird part. Light doesn't care about any of that. Light always travels at the same speed. 186,282 miles per second. Always, no matter who measures it, no matter how fast they're moving. If you're on a train moving 100 miles per hour and throw a ball forward at 20 miles per hour, the ball moves at 120 miles per hour relative to the ground. Speeds add up, but light doesn't work that way. If you're on a spaceship moving at half light speed and shine a flashlight forward, the light still travels at exactly light speed, not 1.5 times light speed. The same. Feynman would ask, how? How can light always have the same speed? The answer: time and space adjust. If light speed is constant and speed equals distance divided by time, then when you move, time must change. Space must change. Both do. Moving clocks run slow. Moving rulers shrink. Not because something's wrong with them. Because time and space themselves are different when you're moving. This is special relativity. GPS satellites must account for this or navigation fails. Particle accelerators see unstable particles that should decay in microseconds survive much longer because time slows down for them at high speeds. But motion isn't the only thing that affects time. Gravity does too, and this is where it gets really strange. Remember those airplane clocks? Two effects competed. The airplane moved faster, so special relativity says time should slow, but the airplane flew higher, further from Earth's mass, in weaker gravity, and weak gravity makes time run faster. Both effects happened simultaneously. The final difference depends on which wins. Gravity affects time fundamentally. Stronger gravity means slower time. Atomic clocks at sea level run slower than on mountains. GPS satellites experience weaker gravity, so their clocks run about 45 microseconds per day faster. Engineers must correct for this constantly. Why does gravity affect time? Because space and time aren't separate. They're woven together into space-time. Mass curves space-time. And where space-time curves, time flows differently. Near a black hole, this becomes extreme. Close to the event horizon, time slows to a crawl from an outside perspective. Watch someone fall toward a black hole and you'd see them slow down, freeze, never quite reaching the edge. Not because they stopped, but because time itself nearly stops for them from your viewpoint. From their perspective? Nothing strange. They fall right in. Time feels normal. Different observers experience wildly different times. That's reality. Now let me address something disturbing. If time is different for different observers, what does now even mean? What does it mean for two events to happen simultaneously? Here's the truth. It doesn't mean anything absolute. Imagine you're on Earth right now. You clap. At this exact moment, someone on a distant planet claps. Same time, right? Wrong? Someone flying past Earth at high speed would see you clap first. Someone flying the opposite direction would see the other person clap first. There's no objective answer. Now is relative. Simultaneity is relative. For events that don't causally affect each other, the order itself can be relative. Causality still holds. If one event causes another, everyone agrees on the order. Light speed enforces this. But for distant, independent events, there's no universal time ordering. This leads to the block universe idea. Past, present, future all exist equally. Time is just a dimension like space. You experience it moment by moment, but it's all laid out. All equally real. Past isn't gone. Future isn't non-existent. They're just other regions of space-time. Feynman was careful here. The math supports this view. The predictions work. But what time ultimately is remains mysterious. You experience time as flowing. You feel the present as special. You remember the past and anticipate the future. But in relativity's equations, time is just a coordinate, a dimension. No flow, no special now. Past and future are directions in space-time, like up and down. Feynman would say we don't understand why our subjective experience differs so much from the physics. The physics is clear, tested, confirmed. But the feeling of time passing from past to future isn't fully explained. There is one clear direction to time, though. Entropy, the second law of thermodynamics. Disorder always increases. Eggs break, but don't unbreak. Ice melts, but doesn't unmelt. The universe has an arrow pointing from order to disorder. Why? The universe's initial conditions must have been extremely low entropy, highly ordered. Everything since has been moving toward disorder. But why those initial conditions? Still unknown. Still an open question. Let me give you one more concrete example of how strange time really is. Muons. Subatomic particles created when cosmic rays hit the upper atmosphere. They're unstable, decaying in about 2.2 microseconds. They're created roughly 15 kilometers up and travel close to light speed. Simple math says they should only travel about 660 meters before decaying. They shouldn't reach the ground, but we detect them at ground level constantly. How? From our perspective, the muons move so fast that time slows for them. Their internal clocks run slow. What feels like 2.2 microseconds to the muon is much longer for us, long enough to reach the ground. From the muon's perspective, its clock runs normally, but the distance to the ground is contracted. The 15 kilometers shrinks to something much shorter. Length contraction. Same phenomenon. Different reference frames give different descriptions, but the result matches. Muons reach the ground. Relativity at work. This isn't theory. Particle physicists observe this daily. So what is time, fundamentally? Feynman would say, we don't know. We know how it behaves, the rules, the equations. But its ultimate nature? Mysterious. Is time fundamental or emergent from something deeper? Is it real or a construct of consciousness? Still debated. What we do know, time is not separate from space. They're unified in space-time, a four-dimensional fabric that curves and warps. Time behaves in counterintuitive ways, but predictable ways. Your intuition is wrong. Evolved for slow speeds and weak gravity, our brains built a model where time flows uniformly. That model works for throwing spears and finding fruit. It fails for the cosmos, but we figured it out anyway. Through mathematics, through measurement, through testing predictions, we discovered time dilates with motion, with gravity. That simultaneity is relative, that space-time curves. GPS works because we account for these effects. Particle physics depends on them. We've built technology on this strange reality. The equations work, the predictions match observations, the theory holds together. It just doesn't feel intuitive. That's our problem, not the universe's problem. Feynman would say that's the miracle. Tiny creatures on a small planet, using mathematics and experiment, figured out the structure of time itself. We can't see time dilation directly, can't experience reference frames moving near light speed. But we deduced it, tested it, confirmed it. The universe is stranger than we imagined. Time bends. Time stretches. Different observers in different reference frames and gravitational fields experience genuinely different amounts of time. Not just different perceptions, different time. This is how reality actually works. Not a theory waiting to be overturned. Confirmed, tested, foundational to modern physics. What were you taught wrong? Everything. Time isn't absolute. It's relative. Time isn't the same everywhere. It depends on motion and gravity. A second isn't always a second. It depends on your reference frame. Time isn't separate from space. They're space-time. The present isn't universally special. Now is relative. The universe is stranger than the simplified version you learned in school, but through careful thought and experiment, we understand it anyway. That's what Feynman spent his life helping people see. Reality doesn't conform to intuition, but we can understand it regardless. That's the power of physics. And now you know.